Really good? Just you can tell me a longer story. It's okay. Uh, I'm I'm a little frazzled as usual, but hopefully this will be good. Let me go over here. This is what I want. Okay. You don't need to know exactly. Well, I'll tell you what. Thursday we're not having class. That's what has me frazzled because Friday I'm giving a lecture in at University of Colorado Boulder, which won't be on online, but it will be covering some of the stuff we're talking about today, which is nice because it seems consistent. So why I'm frazzled is I'm not exactly prepared for Friday. And the lecture, it's like this thing where it's a memorial lecture, so I'm trying to like wrap in the person that's memorializing Bob Lynn, who's a big name in educational measurement, but also like try to have something prepared. So it's yeah, it's one of those weeks. I'll get over it and everything will be okay. Oh, a couple notes about class. Number one, again, homework is due October 3rd, which is a week from Friday. We're going to cover some of the more of the stuff in homework today in class that we haven't gotten to yet. But I think after today, you should be able to do almost everything on homework. Just because I'm leaving town doesn't mean you can't email me. I might be a little bit slower in replying, but please do. This is not, and I will try to be as polite as possible. Actually, as soon as I have a slide deck that's reasonably fine, I'll feel fine. And actually, after this week, my stress level goes back down. So I'm like looking forward to Saturday or Friday afternoon. But that being said, I'll be able to respond to email at some point. Yeah, Jesse.
Did you just say that October 3rd is a week from Friday?
Is it? 2 weeks from Friday, is it?
It's a Tuesday.
It's a Tuesday. It meant to be 2 weeks from Friday. I'll have to double check. It should be. It is next Friday. It should be next Friday. It should be the 6th. Yeah. I'll double check that. Double check what I mean, it will be the 6th. I'll double check the online system. That reminds me. Here we go. You're going to see some of my notes. Stuff to do. Actually, I'll do this. There. You won't see it.
Thanks, Jesse. Yeah, no problem. Like 4 more days. It's all the listening I can do.
Let me put a note to myself. There we go. Okay, and gotcha. Thank you, Jesse. I can't read a calendar evidently under duress, so we'll get this straight. Nope, that's not what you want. You want to see my scores of sports. Let's go back here. So, what do you remember from last week where we left off? Modification indices. How to modify a model that didn't fit well. Cool. The interpretation of everything. That's right. Good. Good. I know that we left off thinking, okay, what do we do next? And that's where we are going to start today, because what we're going to talk about is we sort of left off with right here, right? Assessing global model fit, looking for where things. So typically what happens is you take global model fit. Yeah, most of the time your model doesn't fit your data. So you've got to go and tinker with it a little bit, tweak it a little bit. So that's where you go into localized model fit, right here. And then after that, once you start to get things to work over their modification indices, there were normalized residuals, and I sort of talked about like a holistic picture, if you could kind of tell what was happening, having your items, having your data, and so forth. But let's imagine things did work. Another step to do is to look at, okay, so everything fits, great, right? Model fit is a necessary but not sufficient condition for having a good result. Does that make sense? You got to have model fit to go interpret your parameters, and we talked about why bias might happen. So let's imagine you have good model fit. Does that mean you have great parameters? Not necessarily. What am I looking at here? Take a look at these two correlation matrices. One factor model, one factor CFA fits both of these perfectly, right? And yet, on the left-hand side, you see correlations of 0.1, and on the right-hand side, you see correlations of 0.8. The right-hand side is going to be a much more stronger descriptor of this factor that doesn't exist. All right? You get a left-hand side result, you'll be looking at things where you might have standardized loadings that are 0.2-ish or so. Now, they may be significant, but where that impacts everything that you do comes next. So good model fit, you need to look at your factor loadings to see that they all work. And actually, what I had done, find it here. If I go to the example, so I printed out my example, and let's take a look at the real data version of the example down here. We want the two-factor case. So this is the case where we decided the two-factor model fit pretty well. Remember that? Here. We take a look at all of our loadings, the standardized loadings for each of these. Actually, this is where I constrain them to all be equal. I want to do that. Go up a little bit further. Okay, here we go. This is our two-factor model. We thought, okay, RMSEA 0.057 looks pretty good. CFI and TLI were 0.961, 0.951. Pretty good. This is meeting established guidelines for where it should be. So the next thing we needed to do was look at our factor loadings, and here are the standardized factor loadings, but I also look here at the p-values, right? Because it's possible to have good model fit and not have any of the factor loadings be significantly different from 0. And what you see here is that your factor loadings all have significant differences from 0. That's what you want to see, which means each of the items is contributing to that factor. So why am I talking about this? Why is this important? If you remember the model for, hey, go this way. What are you doing? Why do you have to go that way? This way. There. Okay. If you remember the factor model, okay, we're going to do this. Pen, right here. Remember the factor model for an item? We said that an item y, this is for a person, an item was equal to mu for the item plus lambda for the item, f for the person, plus error for the person item, right? So what we're saying is if we knew the factor score, we could talk about a predicted item response. If the factor loading itself right here was 0, that means effectively that you're missing this part right here, right? You can't say anything about the factor in relation to the item itself, right? So you want your factor loadings to be non-zero. This most of the time it happens, right? Most of the time, almost every item is significant, just in practice. But there are a few times where it'll happen where you'll have 1 or 2 items that are like, not significant, right? And there'll be this weird case where it might have been an item where it maybe not quite, doesn't quite resemble all the other items on the factor, or maybe something else going on to it. So I often get the question, does this cause any problems? And my answer is no, it doesn't cause any problems, because if you have a non-zero, if the factor was there, it wasn't there, right? If it was 0 times the factor, if it was gone, this item isn't going to contribute much information to the factor, right? So the person's score isn't going to get a whole lot out of that item itself, right? Particularly when it comes to the factor score itself. So it's not bad statistically. It's more bad from a sense of, it's kind of an odd thing. People talk about it with respect to validity. Well, I really need this item to load onto this factor because this is really what happens. And if you, more often what you find is conceptually, if that factor, if this really is 0 times the factor, right, for a person, is it loading on there, or is it 0-ish, I should say, is the p-value like 0.12 or something like that? Yeah, it's loading on there, but it's likely to not be a very different from 0 loading. So a lot of times people leave it on there for validity. But does that really mean anything? No, not necessarily, right? So it's kind of an odd situation to be in, but it does happen from time to time. So I guess as a final check, when we get into things, we really want to look at the values of the parameters themselves. Take a look at the effect sizes and so forth. Yeah.
I remember that for using similar code analysis, we looked phone like above 43. Is it the same here?
No.
or-
No, there's no reasonable standard.
How do you decide if it's a good loading or not?
How do you decide it's a good loading? Well, what I like to look at is the following, right? So, this is our factor model. Well, first of all, standardized loading. Let's just put it there. I don't even need to talk about what I like to look at. Who cares about this right here? The standardized loading is good. If you see this plus you find it's the combination of standardized loading plus p-value, right? You can have a standardized loading. If you don't have a lot of data, the p-values aren't going to be, p-value is sort of a measure of how much data you have and how much information you have. So, the standardized loading is really it. And what makes a good item, for me, as long as it's significant, as long as it's different from 0, it's a good item. Right? We don't use the criterion of 0.3 or 0.2. Now, relatively speaking, some items are better than others, right? So, for instance, this 0.653 is the item that has the least amount of information about the SIT-P, the positive situational forgiveness factor. But it's not, it's not a whole lot different than the other two themselves. So does that help? And like the reality of it is, each item is going to have a different amount of information it provides you. And actually, it's going to get even more trippier when we get to a couple weeks from now, because it's not even going to have each item having a set amount of information. Each item will have more information than others in different areas of the scale, right? So what it makes a good item is not necessarily one number. So just hold on to that. That's a good question, all right? So
Theoretically speaking, the variance of like a vector
Mhm.
is not known for us, but if we scale it, there is a ceiling and floor. So
that's right, yes.
So how many items that might be included in the analysis? That's an infinite number.
Well, to get it to have the entire continuum be like we were saying, no ceiling, no floor. Yeah, it'd have to be a continuum. Actually, so with a CFA model, because the item scores are thought to be continuous, right? Remember, we're thinking each item, each Likert response is not 2, 3, 4, 5. It's actually some continuum of values. Theoretically, if you do plug in continuous data into a CFA model, there will be a continuum of results where you won't have a ceiling or floor. It's when you have categorical data where the ceiling and floor effect of the score happens. In particular, when we switch from if you really want to use, and then we keep talking about the CFA isn't really good for categorical data, and it really probably shouldn't be used for Likert data. If you go into and you use a more appropriate model, something with treating the data as categorical, then there are some very understandable combinations of how the number of scores map onto the model that you have. For instance, in an item response model, if you have just binary data, the total number of scores that you're going to get is going to be 2 to the number of items that you have. And speaking of that, effectively, you're going to have the number of scores that are set to be the number of unique, discrete response profiles that you could possibly have. So if you have Likert type items and there's all 5 categories and you have 5 items, it'd be 5 to the 5th power, which 5, 25, 125. Help me out here. Yeah, I don't have the combinatorics or the but that's basically where you're going to have a limit to the number of profiles you have. You're not going to observe all of those, but there will be a ceiling, there will be a maximum value, there will be a minimum value for it. And the thought is that the more items that you have, the more the scores reflect an interval to themselves within that range. And so where we get into problems is in CFA, when you have non-continuous items, but you're putting it into CFA, you have an issue. The other part where we have a problem is if we start to make restrictions on the model, and we sort of saw that, we're going to get to that in just a moment when we talk about the classical test theory assumptions. But each of the restrictions that the assumptions that the classical test theory make involves the factor loadings. If we set all the factor loadings to be equal, we have what's called the assumption of tau equivalence. That severely limits the number of response profiles we have, response response factor scores that we could have. And in the categorical version of that, the Roche model, as I mentioned the cult of Roche last time, the number of response, the number of scores you have is equal to the sum of the items that you have, plus 0, right? So everybody could be at 0, or whatever the lowest score is, so in this case 0. So if you have 5 binary items, there'll be 6 possible scores, right? 1, 2, 3, 4, 5, and 0 if somebody got 0 for all, selected 0 for all. So it puts a limit on what we talk about, but theoretically speaking, the more items you have, the more the tails go. Long answer to a short question. Okay, what do you think? Other questions?
So ideally then for CFA you'd have like a 1 to 100 slider versus like a 1
Oh yeah,
to 790.
yeah, or something that was truly was, yeah, we have a lot more. You'd have a lot more continuing. Now the 1 to 100 slider starts to become like if you have questions online, you've got a slider bar. Like, I think there's a lot more error involved in that, but yeah, that fits more in the assumptions of CFA, definitely.
So it fits more with the assumptions, but in practicality it may not be.
If you think about using it, right? If you imagine what the slider bar does, let's see if I can move this over here. Nope, not that way. This one. All right, you imagine your slider bar, right? Are you happy now? Right? 0. No. 100. Yes. Right? If you had this question, you're like, yeah, pick a value on this bar right here, this continuum, and I pick like right here. I don't know, that's 74 or something like that.
They do it to the quality.
Yeah, like if somebody else does it and they're like, yeah, is that for me, if I'm doing this in Qualtrics, 74 is pretty much the same as like 67 or 78. But what do you think happens in that case, right? If like for me, my 74 is somewhere in that range, where it's certainly not over here by the 50, and it's certainly not over here by 90. That just means we get a little bit more error on the items. But yeah, that's probably, if you can make this work for what you do, it would fit more in the assumptions of CFA, because it'd be more of a continuous measure. Now, with the exception of cases where, the questions that are really polarizing, you get the people who are on this, where people are all 0s or all 100s, like that gambling survey last time. I'll keep it polite. Like, how many times have you, or on a scale from 0 to 100, how many times have you thought about stealing someone's money to go gamble? Right? Everybody's going to be done, right? So we need some other type of model other than CFA to handle when we have kind of these situations where we've got a pile of people at one end, a pile of people at the other, and then stuff in the middle. Call it censored data, sometimes left censored or right censored, truncated data of some sort. But yeah, it does fit with more of it, if you can do it that way. Nothing's ever easy, right? Learn that. It seems like. Other thoughts or questions? All right. No. Okay, so moving on. So we want to check the parameter sizes and whether or not they're significant or not. We want to make sure that all of our estimates are within bounds. What do we mean by that? The issue is when you have a model that looks like it converged, but sometimes it's, I remember we talked about tolerance last time, particularly when you mentioned, Ahmed mentioned collinearity, and I like my head, like brains were coming out of my ears. I was like, no, don't ever bring that up. No, I'm just kidding. But that's sort of one of those situations where you're approaching, like when there's sort of a numerical stability issue, and you haven't tripped whatever the program says this is a problem with, but you're almost there. One of the places where you can see weird results is if you have like a standardized factor loading that's bigger than 1, right? Or less than -1. It's like a correlation of -1.7, right? That can't be. So that just means something's wrong with the analysis. You can interpret that as this doesn't compute, right? There's non-converged, something is wrong somewhere else in the analysis. The other part where this could show up is if you have negative values for some variance. Sometimes it shows up in a factor variance, right? Like if you use a marker item, if you set one of the factor loadings to 1 and you estimate the factor variance, Sometimes you might see a negative number there. That's not good. Negative variance is never a good thing, right? I don't know where that happens to be on the scale of things. But then also, if you use a standardized factor loading, you end up getting sometimes the unique variances themselves become negative. In exploratory factor analysis, that used to be called a Haywood case. You ever heard of that before? But in CFA, it just means it's bad. Something is not working with the model. There's usually some type of deal with the data or the model where it's like, a lot of times where this shows up, if you put the items in the analysis and then put the total score in the analysis, it's going to break because the total score comes from 1 times the sum of 1 times all the items together. So there's already a collinearity built in to it. Okay.
Like, for example, is it going to give us the estimates for that item, like the various, the factor loading, the p-value, the z score, or it would give us like one value and negative?
What you'll find is like if you look here, if you look down at the variances, so this is Levon output right here. If you look at the variance column, somewhere in there, there's a negative. Right. So, is that what you're asking?
Yeah.
So, if you
What I mean is that also is it going to give us like the other estimates like the standard error?
I don't. It depends on the program. I think Levon will warn you about it. I don't honestly know what Levon will do, but some other programs will just report it to you like it's no big deal. And I mention that's a problem because if you get a reviewer on your period, first of all, again, you're concerned about the truth, right? You're concerned about what's happening. That just tells you there's something else going on in the analysis that's not quite right. So look at your data. Look to see if any of your data have correlation of point. When each pair of items has a correlation of 1, for instance. Look to see that your models identify that sometimes the programs will run if you don't properly specify the minimum. I remember how we talked about scale identifiability, right? You had to set a factor loading to estimate the variance. Sometimes they'll let you get away with identification things that aren't quite identified. So take a look at your model. Go back to the basics. Is my data the way I think it is? Is my model the way I think it is? And find it. Usually that eliminates most of the problems. After that, I don't know. Sometimes some programs will report those. So again, being concerned about the consumer of the truth, evidence suggests something's going on with the model. Beyond that, it's really embarrassing to submit a manuscript to review and have an editor or reviewer or whomever point out, yeah, those loadings, that's a problem, right? Or those unique variances, those are a problem. Don't do that, right? So you don't want that to happen. Okay. Thoughts, questions? Okay. So another step in the evaluation is what the heck is going on with our CFA model with respect to this assumption of linearity. One of the things that, again, Lisa Hoffman likes to talk about is how do we take the idea of what our model is saying and compare it with what our data happen to be. So for instance, if you had Likert items that range between 1 and 5, right? So let's do that. And if you were to plot a range of factor scores, in this case a standardized factor, so mean of 0, variance of 1, this is 99% of the distribution of that factor, -3 and 3. You take a look at each of the lines. Each of the lines represents the regression line that comes from the factor model, right? That linear regression that we saw in my notes right here. This is the regression line. If lambda I was right there, this is your regression line, right? This is plotting the predicted values, which comes from the part that's not error of that line. So if you plot them, take a look at what's happening to a range of those values. They're starting to go out of bounds, right? That's not good. That's sort of a very informal check about the idea of continuous data going into the factor model. Right? So if you want to see how to do this, there's some pictures of this in the example at the end, but I'll show you that when we get there. But what you're worried about here is this section right here. You're effectively saying that, yeah, I've got this continuous data, but really, it's starting to see that these things aren't possible. You're predicting values of scores that aren't even on your Likert scale, right? So what that's telling you is probably your data aren't meeting the assumption of continuity. Now again, this is very informal. It's sort of a thing that it stems from the idea, if we had a logistic regression, we're going to see this when we get into binary items. If you predict a 0 or 1 response with a linear regression, quickly you're going to get mean values that are out of bounds, right? A probability of 0.1, 1.2 or negative 0.3, right? And that's what's happening here with the Likert scale. There are ways that you can sort of make this work. A very easy way is a log transform, although I don't like that necessarily, but the main way is this a more appropriate data model. Right? And if you have 5 categories, then a 5-category IRT or IFA model is more appropriate. That's where I would go with. And that's the topic of the next section of class. So,
What's wrong with the log transformation?
the log transformation doesn't work in all cases. And not only that, it still assumes continuity, right? And, you could sort of bend things and make it look a little bit more right. It still gets closer to where it needs to be, but it's not exactly perfect. So, and there's a bigger picture issue with it, is that sometimes, now the log transformation is one of the ones that is a little bit more in bounds because there's something called a log normal distribution, right? It's sort of, if you log transform your data, you're mapping it onto a log normal. And I haven't gone through the moments like the mean and the mean vector is fine. The covariance matrix I think is okay, but the higher order moments I'm not sure about. But the problem is you don't contain all of the effects. You don't contain all the information in your data. So you may change the story by the transformation. And you don't want that to happen. A better practice, and the things that were modern versions of statistics do not talk about transforming data. Transforming data is like you're opening up all sorts of weirdness for results. We'd rather transform the model assumptions than transform the data. Back in the day, back when everybody was like on the Tabachnik and Fidel transformed the data pipe in a train, whoo, right? Let's go transform. We didn't have the methods we have available now. Now, I'm teaching you a set of methods for categorical data, but if your data don't fit like that, there are other methods you can do. You probably have to learn outside the box a little bit, but a lot of the Bayes packages, if you use JAGs or WinBugs or so forth, you can specify the distribution of each of the items. And when you do that, you get a lot better precision with what you do.
So if a IRT model, the chart looks like that too?
The IRT model will have lines that fit in bounds. The data will have to.
So it looks better than
Oh
the
yes,
log
that's right. Now there are other problems. Still cannot. You may have other problems with model fit or other things that are going on, but because the data fits the assumptions of where the bounds happen to be, a lot of the estimates get better, more accurate, I should say. With respect to transformation, if I could tell you one story, I drew this on the board a little bit, but this is my story about it, right? If you had data, if you looked at your data, imagine you looked at you had an experimental design, you gave people 2 groups, and you look at your data, and your data look like this. They are normal, right? But there's a certain section of thought where you're supposed to look at your data, and if it's not normal, you're supposed to transform it, right? Have you been taught that before? Have you been?
Yeah, Fisher's Z transformation is one that I was taught.
Anybody else? Yeah? Well, think of it this way. The transformation is sort of, transformations are never in place without some type of model in mind, right? So let's imagine these are your data. They're bimodal. They're not normal, right? But what if this was a t-test and you had 2 groups, right? What happens with the transformation? The transformation takes this mean, shoves it that way, takes this mean, shoves it that way. You just lose your effect. You don't get a stronger enough effect, right? The t-test, or better yet, an equivalent model is a linear regression with a dummy-coded predictor, right? It assumes conditional normality. And that is, once you condition on what you're predicting with, right? This is maybe the group equals 1 versus group equals 0 over here. Once you condition on that, then the residuals are normal. Right? So this is sort of my problem with a lot of the transformations is they sort of say, yeah, look at your data. If they're not normal, transform it. and the effects will change. I think. I can't say in every case it will, but that's my biggest. I can draw this graph. This problem really is not well. It's another one of my collinearity like pet peeves with the field, is because like even people who are methodologists talk about this. In fact, I was a reviewer on a grant once for a major grant institution where a person, you have to write your name down. So I knew the person's name, and this is a person who's fairly known in the field, proposing methods that would essentially do this. And I put this, I uploaded the file, and I drew something, and I put that in there, and I felt like that hopefully was, look, problem, don't do this. I don't know what happened with what happened with the proposer, but I'm talking about, this is a problem. If you're just hearing it now, it's because it's one of my, I want to change that, right? So don't change your data, change the model is what I'd like to say. And that's what we're going to get with when we get to IRT and when we talk about other ways.
So essentially you are talking about, in this case, because we have a bimodal distribution.
Mm-hmm.
But let us say that we have skewed distribution, whether negativity or positivity. Is the transformation, because it would work.
Why would you transform it in the first place? So if you have a skewed distribution, okay, so the difference is marginal versus conditional, right? So it depends on the analysis you're doing, right? So factor analysis, we want our margin is like the only analysis I know where the marginal data and the conditional data have to be the normal, right? Because the way things work is the factors don't exist and the assumptions and everything. We want our marginal data to be normal. So if it's skewed, CFA probably isn't going to work. What might work is a distribution that allows it to be skewed, right? Alternatively, if you're using like a regression analysis, if you're using a multi-level analysis, if you do look at that, a skewed distribution, marginal data of a skewed distribution may be perfectly fine, because the assumptions of the model are not about the margins, not about the data themselves. It's the data conditional on what you're predicting, right? So if the residuals aren't normal, then that's a problem. Not a big problem, but a problem, right? And so oftentimes that's it. Yeah, this is a very easy, obvious example, like it very rarely happens counterfactual for what I'm saying about transforming it. But it still applies to skewed data. If you have skewed data, the nature of skewed distributions are, and here's sort of the big, backing up a little bit, off topic a little bit, but this sounds like you're interested, so I'll tell you. When you have a multivariate normal distribution, like we've seen only in this class, and if you took my multivariate class, we talked about over and over again. Multivariate normal is a unique distribution in that the mean vector and the covariance matrix are independent, which means anything you talk about with mean does not tell you anything about the covariance matrix. Why that's important is because the covariance matrix helps us govern a lot of what we do with the standard errors of our effects. Right? If you look at the other part about the multivariate normal distribution that's notable is that not only are there these mean vector and covariance matrix, but those are the first two what we call central moments around the mean in this multivariate case. But after that, there's no trivariate. The nature of trivariate relationships is fixed. Right? Something we'd call skewness, right? There is no skewness. Furthermore, the kurtosis is fixed. Well, that's a 4-variable relationship. And quite frankly, you could have relationships of 5, 6, 7, 8. Most of the other distributions that exist, including most of the ones that are skewed or categorical, when you get to the multivariate versions, none of that holds. Mean vector is going to be dependent, or the mean vector and covariance matrix are going to be, there's going to be a dependency. And higher order moments they need to be estimated as well. And so when you see that start to break down, the problem with, you say, oh, what if I transform skewed data? Is that okay? Well, maybe, maybe not. You might want to find a multivariate skewed distribution to be able to fit it, because these higher order moments, or because the dependency of mean vector and covariance, that might be better modeled by the different types of distributions. So now it gets really complicated quick, very quick. But generally speaking, it's an idea of matching your data, what your data looks like, to something that goes with the model. And in this case, for the factor analysis, bring it back to our example here, it's as simple as looking at when you make predictions out of bounds, at least for us. How are we doing? Okay. So let's imagine, again, that you fit your model. Either model fits golden, you're just happy with it, or somehow you modified it to make it work. You checked your loadings, everything was cool. You checked the lines, and everything was in bounds. Right? It's this beautiful result that rarely happens, or you know what happens. It's that guy or that person who's in your cohort who just like somehow that they fall on this great dissertation that it wins awards and everything else, and it's like the data really cooperated, right? That 1 in a million shot that always happens to the person who's no, just kidding. Sound like a jealous person, but no, you know what I'm saying, right? It just happens rarely, and you happen to be the recipient of this luck. What do you do next? Well, up to this point in the class, we've talked about measurement with respect to trying to provide scores for people. So a lot of times in CFA, we're going to provide a score. What type of score do we give? Well, say it. Go ahead and say it. What's that? Well, each score will need a reliability, yes, and that's where we're going with this. Factor score or a sum score. I would say my impression of most research in CFA is the sum score plays out. Use a CFA to demonstrate dimensionality. And then you sort of ignore CFA and you go back to classical test theory and provide a score. And there's some historic reasons for that. You know, if we were using an EFA, then rotational indeterminacy is there. But let's imagine you do that, right? So this is where we get into this portion of the notes. Right here, we can get into, we want to provide reliability for the score. And looking under the heading, gosh, where is it? Calculating reliabilities. If you're on that website, web page, take a look for that. By the way, I'm still working on how to figure, I need to get a table of contents on the website because this is really long for the examples. But if you're looking for calculating reliabilities, a lot of times what we're going to look for is a sum score. Why did you close? Oh my goodness. Attention to it. Okay, here we go. Okay. So we want to come up with a score for people, but we also want to quantify reliability. And you remember what I asked you on the quiz or about that first week of class when I said what to remember about reliability? Uh-oh, I'm losing it. Here we go. Say that again, Jesse. Why don't we? I got a couple of people. I'm glad you remembered. First of all, Jesse, go ahead and. That's right. It's the other way around. Okay. True variance. Observed. All right, it's a proportion of the total variance or observed variance due to true score. All right. So let's take a look at this factor model for a second. I'm going to derive for you just real quick where this is all coming from, right? So if we know that each item looks like this, y for a person item equals mu I plus lambda I f p plus e I, right? That's our factor model. And let's imagine, so for each factor that you come up with in your CFA, you could provide a score, right? And the thought being that, and let's just keep it simple for right now, that each factor is going to have be measured by one, or each item is going to be measured by one factor. Right. Eventually, we're going to get to the factor scores, and I like that much better, but no one else does. So this is your factor model for each item. If you were to go and come up with the sum score, if this model holds, basically what you're saying is the sum of y for a person and item, right? So this is going to be like, all the things I'm doing wrong. If you sum across the items, right, this is number of items, and this would be like the total score for a person. Actually, why don't we call that T? We'll call this T for a person is equal to the sum of all the items, right? So if you do that, and we substitute the factor model in for that now, I'm going to show you where we're going to get our forms of reliability. Okay? So we're going to say this is take this sum, and I'm just going to put I for the total number of items, capital I, pardon me. And we'll have this as mu I plus lambda I factor for a person plus E person item. Okay. Now, if you remember, this is all in parentheses, by the way. Now, I don't expect you to remember algebra, but I will, mainly because I've been there, right? So there's no judgment here. But let me just say, when you have a sum of a set of terms in a parenthesis there, we can distribute the sum, right? So what does this mean? We can say the sum is I equals 1 to capital number of items, and we can distribute it here, lambda I times fp equals 1 to I, and we have a sum of e pi I equals 1 capital I. Okay? All right, so this is what we're saying. Further, we can do a little bit more work. We can change this term right here. I'm just going to drag things down a little bit. Because for a person, the factor score is constant, we can pull that because it's a product of a term that's constant with the thing that varies, right? The factor loading varies. We can pull that FP out. And we can multiply it right here. FP times the sum, I equals 1 to capital I of lambda I. Right? So that's really what that term becomes. So that's your total score.
And this is in the case that we have only one factor.
Yeah, but for each score, for each dimension that you would have in a CFA, that is one factor, right? So in the analysis that we had before, we had the situation positive and situation negative. This is like looking at only one of them, right? And then we do the same thing with both, just separately. Right? Okay, so what part of this we're going to talk about so part of this is due to factor, and part of this is due to error, right? So overall, the whole thing, this whole thing from here to here is total. Your total score comes from that. But this part over here comes from error, right? And this part over here comes from factor. Or in this case, we also, synonymously, we used to call this true score. Right? So, if we want to know these variances, if we want to get reliability, we need to talk about variance components, right? So we want the variance of the total for a person, right? And so now we know the total is this sum of these three terms right here, this part, and this part, right? So the variance, we're just going to do a quick little math. If you add the sum of mu I is a constant, right? We'll just call that constant C here. If you add a constant to a random variable, does it change its standard deviation? No, it just shifts the distribution one way or the other. So this does not contribute to variance. That won't be in the formula. Now we've got the variance of Fp times the sum of lambda I equals 1 to capital I, plus the variance of the sum of error. And now, typically when you have the variance of the sum of when you have the variance of two variables, the variance of x plus y, it's the variance of x plus the variance of y plus 2 times the covariance. But we have said by definition, when we filled our model, that the covariance between error and the factor is 0. So we don't add the covariance. Right? So that is done. So what is this? We can start to rearrange terms a little bit more. We can say this right here, this is a constant times something that's variable. Right? Actually, let me back this up. This was a constant for our sum, but what we know here, this is a random variable, right? Across people. When we talk about variance, we've got to talk about across people. This factor is random, but the loadings themselves aren't random. They are fixed, even though there are some of these constant things. So what we really want to do is say this is the sum. We could, if they're a constant, right? When again that constant multiple. I said before, if we add a constant to a random variable, it doesn't change its variance. But what if we multiply a random variable. Like, what if we said, here's a variable x, its standard deviation or its mean is 0, but its variance is 1. And now we're going to create a new variable that's 2 times x. What is the variance of the new variable? It's 2 squared times the variance of the original variable, right? So what we have here is the factor loadings themselves represent the constant. We need those squared times the variance of f, right? And then again, we still have this variance of error over here, right? This is, right? So now we're starting to get into things that we know are the case. We can calculate what this happens to be, right? We can also know that this whole term over here, this right here is variance of true score, right? This over here is variance of error, right? So now we can go back and do some calculation of reliability. We can say reliability is equal to the variance of true score, which would be the sum of the factor loadings, squared times whatever you estimate the variance of the factor to be, right? And the total variance then is the sum of factor loadings squared times the variance of the factor plus the variance of the error terms. Right there. Right? So there is what our factor model will say the reliability for the sum score happens to be. Now, why I went through this derivation was to sort of slowly walk you through this. Remember where we started. We started with the sum of y. Right, so this reliability derivation applies to the sum score once you've confirmed that the factor model fits. Right, so you did the CFA, saw that for this dimension it's homogeneous, it's one factor. You sum up the items. What's the reliability of that sum score? It's the sum of the factor loading squared times the variance of the factor over the sum of the factor loading squared times the variance of the factor plus the variance of error. Now, yes?
So essentially, like the sum of the factor loading squared is like a kind of standard deviation. You square it to get the variance for that indicator.
For that sum score, yeah. Now, if you have modified your model such that you allowed error covariances, that really applies to the variance of the sum of these things, right? We've been talking about, remember, the variance of x plus y, again, is the variance of x plus the variance of y plus 2 times the covariance of the two. Well, because I didn't talk about error covariances, all of the covariances were 0 in this sum. But to make it work, when you have error covariances estimated as part of your model, you also need 2 times the covariances of whatever items that you have. Whatever, and this is the sum of those covariances. So you need to put those in as well. But what you can see happens if you add error covariances to your model, what happens to reliability for the sum score? It gets smaller because you've now estimated this. Right? Which speaks to another issue. Right? If you added the error covariances to make your model fit, when you calculate reliability using this coefficient right here, it gets smaller. But had you ignored model fit, it wouldn't be as small. Which is what I was saying, model fit and reliability are tied together, right? Model fit comes before reliability. If you don't have model fit, reliability is inflated. Keep remembering that, right? So this is kind of a key point in all this. This statistic is called, sometimes called omega. This is, the person who coined that was Rod McDonald, at least the one I understand to be. There's some debate as to whether or not it's his. I think there's other people. Peter Bentler from UCLA would say, actually I saw him give a talk where he presented someone else's paper that said this guy knew it in the 1970s. Rod McDonald wrote about it in his book in 1999. I'm less concerned about that. I think the way you describe reliability just has to be accurate, and it has to be variance of true score over total variance. Right? But this is reliability for the factor model. So if I go back to my examples, right here, nope, that's not it. Over here, please, and go back to our output. Now you can actually have Levon estimate this for you. You don't have to do this yourself. Hooray, right? So here's the formula we had before, right here. I realized, oh jeez, are you kidding me? Okay, I'm gonna get the hang of this. I thought I was getting better. All I'm doing is just indiscriminately flipping through slides. It's driving me nuts. Okay, note about omega. We're almost there. Okay, get the pen out. This really should be a plus right here, right? So, there we go. The, oh my goodness, this is good. Okay. Forget about drawing. I'm just going to highlight or try to look at it. To use Levon to estimate omega, what we have to do is provide Levon some syntax that basically goes and labels each parameter. We saw this before when I talked about setting things to 1 or 0 when I went in, and sometimes in Levon I could put, when we were estimating the different scale identification of factors, I would go and change a 100 in front of the factor variance. If you don't put an actual literal number there, but if you put a label with characters starting, right? So for instance, in my code right here, L2. There, you can see that. That's good. There we go. L2. I'm worried about this happening. So L2 is a label. And you know, because of this command right here, this represents the factor loading, right? So L2 to Levon means whenever I see the word L2, that's a factor loading. And I'm going to take the value of that factor loading and use it somewhere else. Right, so I'm labeling all of my parameters, L2, L4, L6, L1, L3, L5. Those are my factor loadings. And then my unique variances, E1 through E6. Right? Remember, here for unique variances, the command is the double tilde. You can label every one of the parameters in Levon, and then you can calculate the omega using this new operation, colon equals. Colon equals says, I'm going to define a brand new number, and it's going to be a result of a bunch of other labels that I put in. Okay? So it's going to calculate this for us, and we give it the formula. Here's the sum of the loadings squared, it's the numerator, divided by the sum of the loadings squared plus the sum of the errors. So when we do that in Levon, we estimate the model, you'll see right beside each of our variables now the labels show up. L2, L4, L6, L1, L3, L5. You'll also see the labels show up under the variances. This is really handy to make sure that your label is tying to the parameter you think it needs to be there. But at the very bottom now, we get to see our omega estimates right here. And not only do we get to see the omegas, the thing I like about it is it also calculates the standard error estimate for each of those reliabilities. So you can put a confidence range around where you think the reliability of your test happens to be if you want to. Pretty cool, huh? Takes a little bit more syntax, but you can estimate the reliabilities directly from Levon while you do your model. So what I typically do if you're going to, well, first of all, I don't use sum scores, but if you're to use sum scores because someone is making you, or you believe in them, I'll give you that you may believe in them. That's fair. You create, you do your analysis. You go through the analysis iterations in Levon where you try to get the model to fit. Find the fitting model, then go back, add the labels, add the calculation formula for omega, for however many factors you have. Calculate it, estimate it, and you report that for reliability. What do you think?
Is there a criterion for omega and this level is solid enough?
It's the same 0.8 that I think that 0.8 carries through. It depends on, of course, it depends on your field. But I think 0.8 reliability seems to be a pretty agreeable standard for whatever reason. I haven't done enough research to know whether that's good or not. I know I've talked to people in business before who wanted to develop some type of scale, and they were interested in saying, well, what's the reliability where it's noticeable to someone that, you know, if they take a result test and they take it again, is that fluctuation, is it change, or is it error that you're saying? I don't know if 0.8 is that. I don't know if it should be lower or higher or whatnot. 0.8 seems to be it. Gee.
So quantum alpha assumes tau equivalent,
Mhm.
right? So if I constrain the factor loading to 1,
Not
then I
quite.
calculate the omega, it'll be
Not quite. Actually, let's go into that.
okay.
So, this actually is constrain. You're right. You're along the right path. You're almost there. It's not constraining them to 1. It's constraining the factor loadings to be equal to each other. And if you do that, yes. So, what Jihong was saying is, so if we have a factor model here, where we have our factor loadings allowed to be different. Sometimes we call this, in certain books, they call it congeneric model, or just call it CFA. We can calculate omega. This brings up a question of the relationship of omega with your favorite alpha. Right? So clearly, again, this reliability is for the sum score. Right? So remember, in sum scores only, like omega, alpha, whatever. Alpha is reliability under the tau equivalent model. Right? The assumption of tau equivalence, which effectively says that the relationship of each item with the factor is equal, which in our CFA context means factor loadings are all equal. So if we can go into Levon and constrain the factor loadings to be equal for each of these. And the result will be alpha. And here's how we do that. The label that you put on the item, so here is syntax alpha below. When you use that label again, that automatically makes the parameters equal. Right? So because Levon sees LP for item sit 2, it says, okay, I'm going to put a label of LP on this factor loading for situation 2. And I see LP again for the factor loading for situation 4. In Levon, it's going to say, oh, I don't need to estimate a new loading. I'm just going to join the two together. They're going to be the same number for each. So wherever you put the word LP, then gets the same value. Now, there's some danger to this. If you decide to put LP right here, it'll become the residual variance as well. You don't want that to happen, right? You want to kind of keep factor loadings, keep residual variances. So for here, I'm setting each of the factor loadings for our situation positive factor to be the same value. And down here, I'm setting each of them for the negative factor to be the same value. And I'm leaving everything else the same. All the residual variances are free to be estimated. This is called the tau equivalent model. Right? It's one of the in the history of reliability, there was parallel items, which was Spearman-Brown, and there was tau equivalence, which was Gutman or Cronbach, depending on who you like, alpha. Right? And then there was omega, which was sort of what happens under CFA.
Because we previously estimated the error now, and it is in the denominator,
Mm-hmm.
it would cancel, the alpha would be like the minimum because each error is pre-estimated and cancel the equivalence we set for the.
Well, the error only shows up in the denominator, so it doesn't cancel anything. But having it freely estimated is more accurate. So most of the time, unless you can go and show the model is equivalent.
Because I'm not sure it's correct or
Mhm.
not, but we set the factor loading to be equal.
Mm-hmm.
Let us say that they load in the factor like at 0.7.
Mm-hmm.
And when we really estimate the errors, some error will be higher, depends on the item itself.
Mhm.
So,
Well, depending, it won't cancel. That will not happen. It'll end up. Here's what happens. If the model fits, and the model fits well, let's take a look at our result here. Our estimate is roughly the same. When the model fits, alpha and omega are like decimal places from each other. And the way it works is that omega is going to be higher than alpha. Alpha is a lower bound of omega. Yeah. So, but let's keep going here. What's interesting about this is that alpha is roughly, so here's alpha from the psych package, and here's alpha from our estimates. God, excuse me. This is driving me nuts now. I gotta fix this. Alpha from the psych package, alpha from our estimates are roughly the same. Is what I wanted to come up with. And the roughly is the same if you have missing data. The way that missing data gets treated in Levon versus psych is slightly different, and because of that, what we're getting is not exactly the same. If you have complete data, alpha will be the same if you do what you see right here. If you constrain the factor loadings to be equal and the unique variances to be free, you get it. Question? No worries.
I'm wondering why someone would choose omega or alpha. Like, what would be the deciding factor?
Never choose alpha unless you have to.
Oh, okay.
Yeah. What I'm saying is, what I'm attacking right now, what I'm bringing up alpha for, number one is response to Jihang, but number two isn't, like, it's crazy. I'm bringing it up to try to kill it.
Like you.
What's that?
Like EPSY.
Yeah, that's right. I want to get rid of it. No, always choose the most appropriate reliability measure for what you're doing. The only way alpha would make it work is if that tau equivalent model was shown to fit equally to your CFA model. Can you find that? Can you test it? The CFA model has all the factor loadings freely estimated. The tau equivalent model, where alpha would be, has them constrained to be equal. Sure enough, tau equivalent is nested within the CFA model. So, sure enough, we can use the ANOVA function to test it. Right here. In the heading, Testing Assumptions of Classical Test Theory, if we put in the ANOVA function, the estimates that come from when the factor loadings are constrained, which are right here, the estimates when they're freed, we get a test statistic that tells us whether or not we can constrain them. If this p-value is big, if you do not reject the two, basically you just say that the assumptions of tau equivalence hold in your data. So alpha is appropriate. Now let's talk reality for a second. Nobody cares. You don't need to have tau equivalence hold. You only need to have it hold if you're believing in alpha. There's no reason to believe in alpha because omega takes its place now. Yeah.
But if you're so confident in your model, though, and you do this, and you do have significance, then you can claim tau equivalence.
Yes, you can, but that doesn't buy you. That doesn't make it any better. It doesn't change much about what you're doing for business. It just happens to be the case. The other part of it is, if you're doing CFA, and you still have to do a sum score, calculating omega, if alpha truly held, omega is alpha.
Yeah, right.
So therefore, just doing it like you would for omega would give you the right answer anyway. So.
You often do see both of them reported, though.
Oh, you do? Okay.
And,
So,
yeah, and then they say tau equivalent. Oh, that sounds good.
who cares?
Yeah.
Nobody, honestly, only tau equivalent, and what I'm about to show you is tau equivalency is not even the assumption you have when you sum the scores up. So I'm about to attack the sum score for just a second, too. All right?
So you said don't use omega, but choose.
No, do use alpha.
Use
Yeah,
omega.
sorry, use omega. Use omega.
Oh, okay.
If you have to sum up scores, use omega. If you have to sum up scores, use omega. That's it. If you have to, use omega. And why is that? Because omega is alpha if alpha's assumptions hold. I'll go a step further. I don't have it in the slide. I don't think I have it in the example here. But there is a case, actually it's somewhere in the example. Yeah, there it is. Omega is also Spearman-Brown if the assumptions of Spearman-Brown hold. What are the assumptions of Spearman-Brown? It is the factor loadings are equal, the unique variances are equal for a factor. That's called parallel items. So if you have parallel items, Spearman-Brown is where you probably go for your reliability. But omega will give you that too.
So just to
Yeah.
sum it all up, so if you need to report on the sum scores,
Alpha. I'm sorry, omega.
then
Omega.
use omega, but never resort to alpha.
Never.
Okay.
Never.
So you said
Unless you have to. I just call it reliability. And then everybody goes, oh yeah, it's reliability. So in the reviewer's mind, they're probably thinking alpha is reliability.
Right.
And remember, I'm trying to break that. You can't.
So if you need to report on reliability using the sum scores.
Omega.
Right. Okay.
They call it reliability. And you'll be much better off. That's the question. Yeah.
So omega for subscale scores, but also for if you're going to do a total score, summing items 1 through 40 or whatever it would be,
Yeah.
use omega.
Always. Always. If you have to sum up scores, omega. And you can build it into your code. It'll be output just, you don't have to do any much. It does take a little bit more coding, but it's there and it's nice. Cheap.
After this, there is a plot package called SEM tools can calculate the omega and alpha
Oh, that's good.
directly.
That would be
But
good.
there is no a significant test for the omega. That's the
Okay. Nope. Yeah. It doesn't. Yeah. There's. What. It's nicer. I like it better when you go and get it for the estimate itself. How we doing? So I'm attacking alpha. So what I'm trying to say is this. Everywhere where you've seen alpha before, if you don't see CFA, what happens? If people didn't value, what's that?
Can you repeat that?
Yeah, everywhere that you see alpha reported. Let's imagine you're doing an EFA. You're reading an article and someone did EFA, and they reported alpha. They said alpha is 0.9. Can you believe it? No. There's not enough evidence. It may be true. It may be true. But there's not enough evidence to actually believe it. Right? To actually believe it, CFA, when the assumptions are met, the continuousness is the big thing I'm talking about here, is what you need to believe it. You're going to say, do CFA, so it fits one factor, show it fits tau equivalence, and alpha shows up. I mean, if you're already doing CFA, just keep it in omega. Okay, cool. The other part with it, yeah, sort of.
Yeah, like right here.
Okay, what can I make it go like this? Let's be critical.
It just needs time to marinate.
Oh, okay, gotcha. Because I like the criticism too. I want to hear the arguments about why I'm wrong about this. And believe me, I mean, I'm happy to have them. And I'm not trying to tell you that I'm right about everything. All right, but what I'm trying to build from this is you've got these kind of this hierarchy of things here. Let's do show me the notes. Here we go. Big one. Here's what I look at it as. When you're for sum scores, reliability. Right? There's CFA. Right? Sometimes we call this congeneric model. Some people call it that. I don't know why. Estimate all the factor loadings, right? This is like, sometimes we call it omega. But nested under that, this is like an umbrella right here, right? Underneath that umbrella is tau equivalence. EQUIVAL. Okay, yes. This is what we would call, what we assume to make alpha happen. These are the kind of the assumptions, right? And further nested under tau equivalence is parallel items. Right? And this is Spearman-Brown. Right? Right? So you can always calculate this. So what we're looking at here is 3 different estimates of reliability. But Spearman-Brown's only true when parallel items is met. Right?
But reliability of the sum scores.
Reliability of the sum score.
Of
That's
the
right.
sum scores,
That's right.
Not reliability.
That's right. Reliability for the sum score. That's very good. Yes. Reliability for, always ask for what? Reliability for the sum score.
Yeah.
So if you see a Spearman-Brown, you got to be saying, okay, where are those parallel items? Right? If Spearman-Brown, if tau equivalence happens, then Spearman-Brown and alpha are the same, but doesn't necessarily map onto omega. And if CFA happens, omega, alpha, and Spearman-Brown are the same. The bigger issue is what I was talking about, though, from when we were deriving that formula. What happens if you had error covariance? What if you had something that said the model wasn't fitting right? Right? The model doesn't fit well. Reliability, any of these is overestimated. Right? So this assumes model fit. Right? So when you have model fit, what tends to happen when you have model fit is all three of these line up. It's good. They're roughly the same.
So when you have model fit, then your sum of your error covariances is 0.
Not necessarily. So one of the fixes we could have done to make this model fit better were to add a residual covariance to the model. When we do that, we're in CFA world. The CFA still fits. And we can calculate omega, which would become alpha and Spearman-Brown. It would be fine. It works. It works for that. But what happens is, if you're using just alpha, like you look at the people who didn't do CFA to see the model even fit, if they're in alpha world, they wouldn't know to do that. And so they're going to be overestimating the reliability because they're saying, hey, look at this.
Right, they're not factoring. Okay.
Is that helpful? Yeah. So I'm trying to kill alpha, right? So when the assumptions of alpha are met, you're still getting them with CFA, but you're also getting the model fit detection a little bit better.
So we from AFA to the alpha, what's next?
Sum scores. You want to see the preview of sum scores? Okay, this is a preview because I only have like 2 minutes. Oh my gosh, I've got to be expeditious here. Okay, let's imagine there was a thing called a factor score. All right. This is a case where the sum score and the factor score are identical. Look at that. They're on different metrics. On the left-hand side is situation positive. On the right-hand side is situation negative. The y-axis for both is the sum score for each person. The x-axis is the factor score for each person. Right? Now you'll note I have a standardized factor, so the scores kind of go between -3 and 2, whereas the sum scores go on this. But take a look at the correlation. This is actually estimated. If you go into my syntax to plot this, you'll actually see the correlation function is used. I didn't just type it. I'm actually calculating the correlation. It's 1. Right? So somehow I made it work where the factor scores line up when you use them with the sum score. How are you feeling about that? Okay, cool. When does that happen? What is the model for it? Now hear the bell. The model happens to be the model that we assume for Spearman-Brown. Parallel items. And so what happens when it's not like that, you still get a pretty high correlation when the model fits. But think about what's happening. Someone whose sum score was over here, let's take like a 13, right? They take a look at all the other people that they might switch with, right? A 13, they might have a 13 you think is higher than this level down here. Or take any random 13. There's a good number of people that might be lower than it on the sum score, and there's a good number of people who might be higher on it. The ordering that you get, the order of people, is not the same when you look at it when parallel items isn't whole. And so is that a problem? Well, you get a high correlation. Well, what if you're one of the people where the order switched? Right? If your percentile went from 80th percentile to really 60th percentile, would you feel bad about yourself? Depends on the test, right? Depends on what you're using it for. We're going to continue with that next week. So parallel items has to be held for this to happen. And that doesn't happen either. So. All right, everybody, thank you. We'll stop here. And hopefully I'll get it to work.